Hi, welcome back to Mr. Carroll's classroom. Today we're going to talk about exponential functions and some of their properties. So let's check it out. Okay, so we're going to start with a very basic foundation here, the basic formula for an exponential. And really the heart of an exponential is the base here. It really tells us a lot about an exponential function, which we're going to see here in a second. But also, what makes it an actual exponential is that we are plugging in for the exponent. Okay, so and a out here is really just some kind of constant. All right, so let's go ahead and take a look at some of these pieces and define them. And as we're doing that, I just brought up some real examples with real numbers. So you can see here I have f of x is equal to 1/2. In this case, the 1/2 would be the a, and then the 3 would be the b, and then to the power of x, and so on and so forth. So g of x, 2 would be a, 1.15 would be the b. Basically, the number out front is a, and the number inside the parentheses is going to be your base. Okay, so let's go ahead and talk about what these are. So first of all, a and b are constants. However, a on the outside really just stands for your normal transformation for an a, which is it's going to like vertically stretch or shrink and it vertically flip this graph. But other than that, it really doesn't do too much. What we're really after here is the b, which is the base, and we'll talk more about that in a second. The x value is the domain. Why is it the domain? Because that's what we're plugging in for, right? We're going to plug in an x, which means that what we're going to get back, f of x, or the y value, is going to be the range. All right, and we'll discover a little bit more about those as we look at the graphs. And then finally, we have some restrictions here. A cannot be 0. Why is that? Well, if a was 0, then it would wipe out the entire equation and you would just get 0, right? A times, or 0, if a was 0, 0 times anything is just 0. Also, b cannot be 0. And why is that the case? Well, if the base were 0, it would be 0 to the power of whatever. It doesn't matter what x it is. 0 to the first power is 0. 0 to the 100th power is still 0. So you'd still end up with just 0, which would again wipe out the entire exponential, just leaving it with a constant. And then finally, b can also not be 1. So why cannot it not be 1? Well, for pretty much for the same exact reason. 1 to the power of anything is just 1, so we would end up with a times 1, which is again just a constant, wiping out that exponential. So those are our restrictions. There are actually a couple more restrictions that we'll kind of talk a little bit about later on. Okay, so let's go ahead and talk about this base right here, because a lot of an exponential, or at least the way it behaves, is surrounded around what this value actually is. Specifically, if it's greater than 1, then it's going to increase rapidly. If it's between 0 and 1, then it's going to decrease over time. Okay, so but anyways, there are a lot of names for this base. I'm going to mostly refer to it as a base. However, if you had just gotten out of a geometric sequences unit, then we would call it R for the common ratio, which is a very similar thing. Or you might hear it referred to as the growth rates. All right, or you might hear it referred to as the scale factor, or the exponential factor, or it could be the exponential growth factor. And if I throw in this word growth right here, then that basically means that, hey, this thing, it's inferred that this thing is growing, which means that the b must be greater than 1, because that's the only circumstance in which it would be growing. It could also be referred to as the exponential decay factor. And decay infers that b is going to be some kind of fraction between 0 and 1, because you're repeatedly multiplying by a fraction, and so you're getting smaller and smaller and smaller. Okay? You also might hear in different problems the terminology percent increase and percent decrease. And we have to kind of decipher what this means in order to come up with our b value. So for example, if in a problem they said, well, whatever happens to be, maybe it's like a, I don't know, a savings account or maybe a grade percent average or whatever, it doesn't really matter. But if they said that this is increasing by 5%, maybe year after year or month after month or whatever it happens to be, but if it's increasing by 5%, then we have to convert that into some kind of proper b value. And you have to realize that if something is just 100% of what it is, well, 100% is equivalent to a b value of 1. It's not changing. But if it's increasing by 5%, then it's 0.05 on top of the value of 1, on top of that 100%. So in other words, it's 105%. But we do not express our b values as percentages. We have to convert them into decimals. So in this case, it would be 1.05. That would reflect a percentage increase of 5%. Now, if they refer to a percentage decrease, let's say, for example, they said, well, this thing is decreasing by 20%, every some kind of, increment of time or whatever. For example, maybe you're like, I don't know, landing a plane or something like that. The plane is kind of swooping down, and maybe they say, well, it's decreasing, the height or the altitude is decreasing by 20% every minute, something like that. What does that mean? Well, as far as a b value goes, well, that means if it's decreasing by 20%, remember, we started 100%. If we're decreasing by 100%, then that means every subsequent minute in that case, we are going to be at 80% of what we were previously were. Okay, so in this case, the b value would be 0.8, all right, when we convert 80% into a decimal. So in essence, if you hear percent increase, you're going to add that to 100%, so 5% plus 100%, or 100% plus 5%. And if they say a percent decrease, then you're going to subtract, so it'll be 100% minus 20%. And of course, you have to convert those percentages into decimals in order to use them in our equation, in our exponential. Okay? All right. So a lot of terminology there, a lot of words that we can use. Okay, so let's go ahead and start taking a look at what these things look like graphically speaking, so we can get a better understanding of how they behave. So probably one of the most basic exponentials that we have is y is equal to 2 to the x. And if you're wondering where the a is, it's still there. It's just 1, okay? 1 times the base, in this case b would be 2, to the power of x. So let's go ahead and figure out how this behaves, and we're gonna investigate this using some good old-fashioned x and y table. All right. So using an x and y table, if I plug in the values of 3, 2, 1, and 0, then what do I end up getting? Well, of course, if I plug in 3, that's 2 to the third power, right? And 2 cubed is 8. 2 squared is 4. 2 to the first power is 2. And anything to the 0 power is 1. Okay, so we could plot those, and but we're going to actually continue on with our xy table. And the real question is, these are going downwards, right? I'm plugging in x values as I go down in x values. My y values are going down as well. So the question is, are these going to be negative values below here? Let's go ahead and keep plugging in to find out. So if I plug in -1, 2 to the negative first, 2 to the negative second, and 2 to the negative third, then I actually don't get negatives back. I end up with 1/2, 1/4, and 1/8. Why is that? Remember, based on our exponential properties, 2 to the -1, if you have a negative, then you have to, if it's in the numerator, you flip it to the denominator and vice versa. So that's actually 1 over 2 to the first power, or just 1/2. In other words, this one right here, 2 to the negative third, would be 1 over 2 to the third, or 1/8. Okay, so yeah, so the question is, I guess, are we ever going to get negatives out of here? Well, based on the way this is going, the answer to that is no. So let's go ahead and take a look at the actual graph now so we can see the behavior. Okay, so here we are, and you can see like at 3 right here, it would go all the way up past this, all the way up to 8. But anyway, basically all these points will be on here. But what we want to note is that as I was plugging in x values as we go down, it seems to be getting closer and closer to the x-axis. And that is the behavior here. In fact, it will get closer and closer and closer to a y value of 0, but it will never actually get there. And that is part of the fundamental behavior of exponential functions. Now, you might be asking, okay, well, that's y is equal to 2 to the x. Well, what if I change this power to, I'm sorry, this base to something else? Like maybe like 1/2. What if I have y is equal to 1/2 to the x power, some kind of fraction? What is that going to look like? Am I going to get something with negatives? Well, let's take a look. And here we are, so I did all the work for you here. So if the base is 1/2 and we went ahead and plugged in these values, then we actually, let me kind of flip back and forth here so you can see. So here was 2 to the x, and here's 1/2 to the x. So 2 to the x is going up and up and up as time goes on. And the base of 1/2 is going to go down, down, down as time goes on, which makes sense. Every time we go further to the right, we're basically having the previous value. And why does this work, by the way? Like for example, if I took 1/2 to the third power, let's just do that below here real quick. 1/2 to the third power is equivalent to 1 to the third power over 2 to the third power. And 1 to the third power is just 1, and 2 to the third power is 8, getting us our fraction of 1/8. Okay, so there we go. All right, let's continue on. So those are some basic graphs there. Let's go ahead and push ourselves with some more examples here. So in the beginning, I had these 4 examples up at the very beginning of this video. F of x is equal to 1/2 times 3 to the x. G of x is equal to whatever, h of x, and then I of x. Let's go ahead and take a look at these graphs. Now, I want you to notice, first of all, that all of these actually stop at the x-axis, and even though it might look like they go past them, that's really just because these are, I drew these as really thick lines, but they actually don't cross the x-axis. And as you can see here, let's go ahead and kind of label some of these. It's really not so much about the a value here. It's really about the b value, the base. That really kind of determines the overall shape of this thing. And so for this blue graph, if you look at this over on the in the graph, it is, as time goes on, as x goes from left to right, it is going to increase rapidly. Well, why is that? Well, that's because the base is a positive number above 1. And so the bigger that number is, the quicker it is going to, or the more rapid it is going to increase. This one right here, the red graph, it is still increasing over time. However, it's increasing at a slower rate because its base, or its rate of change here, is only 1.15. Okay. What about the fractions? So the fractions are actually going to start high and then start decreasing over time. So this one is the green one. And this fraction is a very kind of a smaller fraction, 1/3 or 0.33. So every subsequent value is going to be 1/3 of the one before it. So it's going to decrease at a pretty rapid pace there. This one, however, the purple one, is going to decrease at a slower pace because it's going to be 80% of the previous value as we move from left to right. Okay, so there we go. So hopefully this gives you an idea of how these exponentials are being shaped and formed and why they are the way they are. Now, what about those a values? I said in the beginning that the a values are actually the same a value in any transformation type of form, meaning that a value, it does have an effect, but it's really just a vertical stretch or compression, or if the a values happen to be negative, I just have the exact same problems or exact same functions down here, except they're all negative, the a values. All that's going to do, like it typically does to any function, is it's going to flip every single one of these functions over the x-axis. Okay. All right. So let's go ahead and continue. Because if we can get a negative a value and it actually plays an effect on the graph, the natural next question is, what about a negative base? Can that happen? I've already given you some restrictions. I said, okay, the base can't be 0 and it can't be 1. If it's between 0 and 1, if it's a fraction, then that's fine. It's just decreasing along the way. If it's above 1, that's fine too. It's just increasing. But what if it's negative? Can we have a negative base? Well, the short answer is yes. And I would highly encourage you to investigate this a little bit. The problem is you can, but you would end up with these complex solutions. And we are going to not deal with any of those types of cases in this particular class. But if you are interested, I would highly encourage you just to come up with a real basic function, exponential function, maybe like -4. Actually, I have an example here with -4. So like y is equal to -4 to the power of x, where the base is -4. And the issues are, well, let's just talk about them really quickly. So like, for example, let's say x was 0, right? -4 to the 0. Well, anything to the 0 power is 1. So we get +1. So far, so good, right? Well, what if x was 1? Well, -4 to the power of 1 is -4. Okay, so I'm already flipping actually back and forth. I went from 1 to -4. And actually, that's what you will find here, this going back and forth between positives and negatives. However, it's not just about plugging in 0, 1, 2, 3, 4, all of these integer values for x. What about everything in between? What if I plugged in 1/2? So that would be -4 to the power of 1/2. And actually, we can do the power of 1/2. That is actually a square root. And as we know, the square root of a negative number gives you an imaginary number. In this case, it would be 2i. So, if you're again, we will not deal with these in this class. However, if you're interested, this particular graph actually would look like this, where that purple part would be the real solutions that you get, and then the orangish yellow part would be all of your imaginary solutions. So so you end up with this really complex, interesting, but definitely lying in the realm of complex numbers there. Okay, but anyways, so we're not going to deal with negative b's at all in this class, so don't worry about that. You will have to deal with negative a's, but that is simply just a transformation where it's getting flipped vertically. All right, let's continue on. Let's talk about behavior. All right, how do we actually put into mathematical notation the behavior of exponential functions, or I should say the graphs and the graphs of exponential functions? So first of all, I have this example here, which is just f of x is equal to 1/2 times 3 to the power of x. And really, like we said before, the really important thing here is that the base is +3, which is greater than 1, which means that this thing is going to increase as we move from left to right. And so let's go ahead and write down everything we can write down, I suppose, about this this particular graph. So first of all, what is the domain? In other words, what values of x can I actually plug in? Well, actually, I can plug in any x value. I can go all the way to the left and plug in x values and find a y, and I can go all the way to the right and continuously plug in x and get y values. So that means that the domain goes from -infinity to +infinity, or you could say all real numbers, and that's the symbol for all real numbers. So what's the range? What y values do we get out of this? Well, in this case, we know that this thing doesn't actually cross it doesn't actually cross the x-axis. We have this horizontal asymptote, and actually, I think I did actually skip that. Let me go back and show you very quickly what the horizontal asymptote actually looks like here. Hang on one second. Give me a second here, sorry. And I don't think I actually turned this on, but before, when I was flipping back and forth with y is equal to 1/2 x and 1/2 to the power of x and 2 to the power of x, both of these have this invisible line, this horizontal asymptote, which, well, that's why it's a dotted line. It's not really a part of the graph, or at least not a visible part of the graph, okay? All exponential functions have a horizontal asymptote. These simple functions happen to be on the x-axis. However, in a future lesson, we're going to go ahead and transform this by moving it up, down, and left and right, and all that kind of stuff. And the horizontal asymptote will move with those transformations. Okay. So, but anyway, let's go back and finish this up. Okay, so the range. So we know that this thing does not cross the x-axis. That is a terrible line there. So the range is for the y values, and remember, we always go from negative to positive. We get y values starting at 0, but not including 0, because it approaches 0, but it never actually touches it. So from 0 up to positive infinity for our range. All right, what else? What about our end behavior? All right, so as x approaches positive infinity, meaning as x goes further to the right, what do our values our y values yield as x approaches positive infinity? Well, as x goes further and further to the right, the y values are going to go further and further upwards at an exponential, alarmingly exponential rate. So we would say that f of x approaches positive infinity. And as x approaches negative infinity, as we go left farther and farther and farther, where do the y values approach? Well, in this case, they're getting closer and closer and closer to 0. So we would say f of x approaches 0. So as x approaches negative infinity, the function approaches 0. And then finally, the last way we can describe this is we could say that f of x is increasing, meaning as we move from left to right, the overall graph is going up and up and up, so this thing is increasing. Okay, let's do one more here. So now I've got a value, let's see here, I put a negative in front of this a value, so basically this is being vertically flipped or reflected over the x-axis. So let's go ahead and again describe this graph using the exact same terminology. So first of all, what is the domain? Well, the domain in this case is all real numbers. We can plug in x values along the entire range of the x-axis and get y values back. And the range in this case is all below the x-axis. And remember, we always start with the negatives and then go upwards. So we're starting as low as it goes, negative infinity. And how high can we go and still get y values? Well, we can only get to 0, but it is not included, which was why we have the parentheses and not the square brackets. The end behavior. Whoops. So the end behavior. So as x approaches positive infinity, what does the function approach? Well, in this case, as x goes further and further to the right, the y values go further and further down. So f of x will approach negative infinity. And as x approaches negative infinity, as we go left, 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 what are the y values, or what is the function approaching? In this case, it is 0. Okay, so there we go. There is our lesson on really an introduction to exponential functions, how they behave and how they look and how we can describe them. Hopefully this lesson was helpful to you, and hopefully I will see you in the next one. Bye now.